Hello and welcome to lesson number 8, Trigonometric Identities. So, to start off, before we talk about trigonometric identities, we need to first talk about identities in general. What is an identity? Identity is an equation which is always true for all possible inputs. An equation which is true for all possible inputs. Now, what do I mean by something like this? Well, for example, the equation a plus b squared is a squared plus 2ab plus b squared is always true no matter whatever the a and b we substitute into here. No matter what the a and b are in this case, this equation will always be true. In contrast, something like x squared plus 1 is equal to 0 has a certain finite set of solutions. There's only certain values of x that we can substitute into here in order to get that x squared plus 1 is equal to 0. Considering another example, an identity would be something like this. X is equal to x. X is equal to x is an identity because no matter what value of x we substitute into here, we get a truth. X on the left is equal to x on the right. Similarly, we can get that something like, let's say, x squared is equal to negative x squared is also an identity. It is always true. No matter what value of x you substitute into here, it is always true. Something that's not an identity is something like x squared plus 2x plus 1 is equal to 0. This equation does not work for every possible value of x. For example, try x equals 2. If we try x equals 2, then we get 2 squared plus 2 times 2 plus 1, which is 4 plus 4 plus 1, which is 9. 9 is not equal to 0. This does not work. The solution is x equal to negative 1. We do this by solving the equation. So here in this case, x squared plus 2x plus 1 is x plus 1 whole thing squared, which is equal to 0, which then taking the square root means that x plus 1 is equal to 0, meaning that x is equal to negative 1. X is equal to negative 1 is the solution to the equation x squared plus 2x plus 1 equals 0. An identity does not have this property. You cannot find a solution to an identity because an identity is true for every possible value of the inputs that you could substitute into it. So that's what I mean when I say an identity is an equation which is true for all possible inputs that we could substitute. We could substitute any input within our input space and we would get a truth. The left side would equal to the right side. So now, let's move on to some trigonometric identities. The first identity, which we proved a while earlier, it's there, I'll link it once again in a card in the top right, is that given sine of theta and cosine of theta, which I'm going to illustrate with this circle, if this hypotenuse is of length 1 and we have a 90-degree angle here, then this would be cosine of theta. This length on the bottom would be the base would be cosine of theta and the height would be sine of theta. And sine squared of theta plus cosine squared of theta would equal to 1, and it would equal to 1 for all values of theta. It would equal to 1 for all values of theta, meaning that sine squared theta plus cosine squared theta equal to 1 is an identity. This is true for all possible values of theta. So therefore it's an identity. This is what we call a Pythagorean identity, and there's 3 Pythagorean identities which are all the same exact equation expressed in different forms. There is a little catch and we'll get to that. Right now, this is first one is true for all theta in the real numbers. The second identity can be found by dividing the whole thing by cosine squared theta. So if we just do that, we get sine squared theta divide by cosine squared theta plus cosine squared theta divide by cosine squared theta is equal to 1 divided by cosine squared theta. So here sin squared theta divided by cosine squared theta is sin theta divided by cosine theta squared. Sin theta divided by cosine theta is tan theta. So sin squared theta divided by cosine squared theta is tan squared theta. Plus cosine squared theta divided by cosine squared theta is simply 1. And on the right side we have 1 divided by cosine squared theta, which is 1 divided by cosine theta whole thing squared. 1 divided by cosine theta is secant of theta or sec theta. So that thing is squared, which means we have secant of theta squared on the right side. This is another identity. It is true for all values of theta, except we have a little problem here. Since we are dividing by cosine theta could potentially be 0 at certain values. Cosine theta could potentially be 0 at certain values, and in fact cosine theta is 0 at certain values. So we should not divide by a 0 in this case, which is why we have to make the restriction cosine theta should not be 0. So that means that the second identity here could only be taken really as properly valid given that cosine theta is not 0, because it's not good practice to divide by a 0, a potential 0. But for now I'll just label this one also as being an identity and true for all theta in the real numbers, even though we have the issue of some theta causing a divide by 0. We'll skip over that and just say this is also an identity and it's true for all of the real numbers. The other identity, I said there were 3 Pythagorean identities. The other Pythagorean identity can be found by taking the first Pythagorean identity, sin squared plus cosine squared is equal to 1 for all thetas, and dividing it instead of cosine by cosine squared theta by sin squared theta. So we take sin squared theta divided by sin squared theta plus cosine squared theta divided by sin squared theta is equal to 1 divided by sin squared theta. So we divided everything by sin squared theta. Note again we have the thing where we should have that sin theta not equal to 0, because otherwise we are dividing by 0. We will ignore this for now, but I'll write it down on the right. We will ignore this and simply divide the two and get an identity. And the identity we get is that on the left side, sin squared theta divided by sin squared theta is 1 plus cosine squared theta divided by sin squared theta is cosine theta divided by sin theta whole thing squared. Cosine theta divided by sin theta is cotangent of theta. Cotangent of theta squared is therefore what we have to put here. Cotangent squared of theta is equal to 1 divided by sin squared theta is 1 divided by sin theta squared. 1 divided by sin theta is cosec theta. So therefore on the right side we have cosec squared theta. Also, by the way, I would like to take this moment to tell you guys, we write cosec squared theta like this. We write cosec or the cosecant of theta like this as 5 symbols COSEC. In many parts of the world, it is common to write cosec theta as CSC. So if anyone's watching from anywhere other than Sri Lanka, this is what we're writing here. COSEC is cosec theta, cosecant of theta. If you write cosecant of theta like this, it's alright. I mean, it's your convention, it's how you write it. But to all my fellow students who might be a little bit confused, note that in other parts of the world, cosec is written as CSC, not COSEC. I'm telling you right now, just so you don't get confused ever. So there we go. And this here, 1 plus cotangent squared theta is equal to cosecant squared theta is another identity. This is also true for all theta and the real numbers. These 3 right here, which are all really the same identity, but we're dividing by cosine squared and cosine squared, these 3 identities are what we call the Pythagorean identities. Note that there's a little issue where we are dividing by 0 in some cases, which we will for now just ignore and write these other 2 as identities true for all theta element of the real numbers, because we are not going to really get on to why they are true for those divide by 0 cases also. We are just going to skip over that. The first one, of course, is true for all theta element of the real numbers. There's no issues in the first one. The other 2 have divide by zeros because tan and secant tend to infinity at certain values. So do cot and cosec. So that's it. Let's now go to some other trigonometric identities other than these three Pythagorean trigonometric identities. Alright, so now let's go over the next set of identities that we're going to discuss here, which are the identities of adding two angles together to give you something else. So let us consider something like this situation. We have a line here, we have another line here, so clearly there's an angle between these two lines. This angle, however, is going to be in two components like this. So this angle is split across two different angles. I'm going to call this first angle angle A and this second angle angle B. And I want to compute the sine of the angle A plus B, the cosine of the angle A plus B, and the tangent of the angle A plus B. So we have this. This is a 90 degrees between these 2 points. And I want to find what the sine of angle A plus B and the cosine of angle A plus B and the tan of angle A plus B are. So we're going to define some points for this. Let's define this point as the point P. Let's define this point as the point Q, this point as the point R, and this point as the point S. So here what I want to find are sine, cosine and tangent of these set of points. So sine of the A plus B angle, I'm going to just assume for now that this length PS is 1. That will make our ratios of trigonometric ratios easier to figure out. So sine of A plus B. Sine of A plus B will be the opposite side divided by the hypotenuse. In the right angle triangle PQS, the opposite side is QS and the hypotenuse is PS, which is 1. So we have sine of A plus B is equal to QS divided by 1, which is simply QS. So sine of A plus B is QS. Similarly, with our nice factor of 1 as the hypotenuse of PS, cosine of A plus B also becomes simple. Cosine of A plus B is simply the ratio of the adjacent side, which is PQ, divided by the hypotenuse, which is PS, which is 1. So simply cosine of A plus B is PQ divided by 1 or just PQ. And tangent of A plus B, tan A plus B, is the opposite divided by the adjacent. The opposite is QS and the adjacent is PQ, so we can just write QS divided by PQ. So we want to try to find sine of A plus B, cosine of A plus B and tan of A plus B. But we want to find them also in terms of sine A, cosine A, tangent of A, and sine A, cosine B and tangent of B. Why? Well, you will see why in a little bit. But we're going to try to find each of these values, sine of A plus B, cosine of A plus B and tangent of A plus B, in terms of sine, cosine and tangent of A and B. So to do this, we are going to need to do a little bit of construction. We are first going to construct the perpendicular from point S to the line PR. So we're going to construct it. It will look something like this. This is a 90 degree angle here, 90 degrees, and we've constructed it. Let's call the point of intersection here of S, the line from S and PR, as the point T. Let's now construct a vertical down from T down to the line PQ. So because this is a vertical and PQ was a horizontal, this is also 90 degrees. These two are perpendicular. Let's call this point here, this intersection of this line drop down from T and PQ, to be U. And finally, one more construction. Let's draw a horizontal from T until it touches QS. So here, drawing the horizontal from T until it touches QS, it will touch right there. And let's label this point finally as the point V. This is the point V. So now we are almost done. We just have a little bit more work to do. Let's consider some more angles. So here, what I'm going to do, I'm going to consider the triangle PTU. Inside of triangle PTU, we can see this angle is A, this angle is 90, which means the angle here, angle PTU, is 90 degrees minus A. Now consider this. VT is a horizontal and TU is a vertical. That means angle VTU is 90 degrees. Here it's 90 degrees. Meaning this angle here plus this angle is equal to 90 degrees. but this angle is already equal to 90 degrees minus A, which means that this other angle here, VTP, must be equal to A. And then there's another one we need to do actually. Considering the angle RTS. RTS is a 90 degree angle, which means this angle here has to be 90 degrees minus A. So the angle STV is 90 degrees minus A. And now considering the triangle SVT, we have 90 degrees at here, which means that if this is 90 degrees minus A, then this other angle VST has to be equal to A. And I promise that's it. We're done with the constructions. Now let's actually go on to try to solve sine of A plus B, cosine of A plus B, and tan of A plus B in terms of sine, cosine, and tangent of A and B. So looking at this thing, we can see PS is 1. Consider triangle PST. Within triangle PST, we have 90 degrees at T, which means PTS is 90 degrees. And considering the angle B at the point P, we can see that the sine of B is equal to the opposite, which is TS, divided by the hypotenuse, which is PS, which is 1. So therefore the sine of B is simply TS. So sine of B equal to TS means that TS is equal to sine of B. The length TS is equal to sine of B. Similarly, from the same logic, the cosine of B, cos B, is equal to the adjacent side divided by the hypotenuse. The adjacent side is PT, the hypotenuse is PS, which is 1. So cosine of B is PT divided by 1. So cosine of B is PT. Therefore the length PT is equal to the cosine of B. Now we're going to do a little bit more geometric reasoning, considering the triangle PTU. In triangle PTU, we've just found out that the hypotenuse PT is cosine of B. We're almost done here. We're almost done for considering some of these. Considering TU and PU, considering these two lengths, what is sine of A? Sine of A is the opposite divided by the hypotenuse. In the triangle PTU, the opposite is TU and the hypotenuse is PT. So therefore sine of A is the opposite, which is TU, divided by the hypotenuse, which is PT. We just found that PT is cosine of B. So therefore sine of A is TU divided by PT, which I'm going to directly write as cosine of B. Similarly, what is the cosine of A? Cosine of A. Well, the cosine of A is the adjacent divided by the hypotenuse. In this case, for the cosine of A within the triangle PTU, it is adjacent divided by hypotenuse. The adjacent here is PU, the hypotenuse is PT. So therefore cosine of A is PU divided by PT, and PT is the cosine of B. So we have cosine of B. And now we are almost ready. We just need to do one more little thing. We need to consider the triangle STV. Considering triangle STV, which I'm going to draw another vertical bar to consider that triangle. Within triangle STV, we can see that we have two other side lengths, SV and TV. Let's try and find out what SV and TV are. So considering sine of A and cosine of A within this triangle, let's try to figure out what these two values are. Within the triangle STV, sine of A is opposite, which is TV, divided by the hypotenuse, which is TS, and we found TS to be sine B. So therefore sine A within the triangle STV is TV divided by sine B, which is the hypotenuse TS. Similarly, the cosine of A within the triangle STV is the adjacent, which is SV, divided by the hypotenuse, which is TS. So we have SV divided by, and TS in this case is found to be sine B. So that's that. Now we have all the tools we require. All we need to do is to try and express sine of A plus B, which is QS, cos of a plus b, which is pq, and tan of a plus b, which is qs divided by pq, in terms of the side length that we've already found. So we have found certain bunch of side lengths. We found ts, pt, we found tu, we found pu, we found tv, and we found sv. However, we found them? Well, we've equated them to some sine and cosine of a and b, which are known. So, if we look at sine of a plus b, it is qs, the height qs, which is from here to here. This height is what we need to find. Notice that this height can be formed by the two heights tu and sv. Have you noticed that? Good. Now that you've noted it, we can write that qs is equal to tu plus sv. So qs, which is the sine of a plus b, which is equal to qs, is also equal to the heights tu plus sv, is equal to tu plus sv. Now, taking this, we know what tu is and we know what sv is. From the above, we can see that sine a is equal to tu divided by cosine of b. So therefore, multiplying both sides by cosine of b, we can see that tu is equal to sine a times cosine of b. So doing that, we can substitute tu for sine of a times the cosine of b. Plus, now to substitute sv. Sv is over here. If we consider what we have cosine of a is sv divided by sine of b. Multiplying by sine of b, we can see that sv is equal to cosine of a times the sine of b. So sv we can substitute as cosine of a times the sine of b. And we have accomplished our mission here actually. We can see that we have expressed sine of a plus b in terms of sine, cosine and tangent of a and b. We didn't require tangent here, we only required sine and cosine of a and b, but that's alright, we just wanted to express it in some way. And we have expressed it in some way successfully, as the sine of a plus b is equal to sine of a times cosine of b plus cosine of a times the sine of b. And note, this right here, what we've derived, is an identity. This thing, this equation, sine of a plus b being equal to sine of a times cosine of b plus cosine of a times sine of b, is something that is true for all possible inputs of a and b. This right here, which I'm going to mark with a square around it because it's an identity, this is an identity. It is a true for all a comma b, for all a and b in the real numbers. Any pair of a and b that you can possibly think of, this statement will be true. Similarly, if we consider the cosine of a plus b, which is pq, and we try to express pq in terms of the lengths we know. Looking at the lengths we have, we can see that pq is equal to the total length pu minus the length qu. We can see that that's true. And we can also see that because we constructed VTUQ, and VTUQ is a parallelogram, we can see it's a parallelogram because QV and UT are vertical, which means they're parallel in the vertical direction, and VT and QU are horizontal, so they're parallel in the horizontal direction. By the fact that VTUQ is a parallelogram, we can then see that QU is equal to VT. Therefore, the length PQ is PU minus VT. So going down here and writing that down, cosine of a plus b, which we wrote down as PQ, is equal to PU minus VT. Sorry, it should be capital T, VT. In fact, I'll write the V also as bigger capital, VT. So, PQ, or the cosine of a plus b, which we found earlier, is equal to PU minus VT. So, considering the side lengths PU and VT, which is here I've written as TV, VT and TV are of course the same length. Considering these, Pu is cosine of A times cosine of B. Considering what we have cosine of A is Pu divided by cosine of B. Multiplying both sides by cosine of B, we can see that Pu is cosine of A times cosine of B. Substituting that in, we can see Pu is cosine of A times cosine of B. Minus, what is Vt? Well, in this case we have that Tv is equal to sine of A times sine of B. By multiplying both sides by sine B in this equation, we can see that Tv is equal to sine A times sine B. So then we have cosine of A times cosine of B minus sine of A times sine of B. Again, we have accomplished our mission because we have written cosine of A plus B in terms of sine of A, sine of B, cosine of A, cosine of B, tangent of A and tangent of B. In this case, we didn't need tangent of A and tangent of B. We have accomplished it with simply just sine and cos. So alright, there's no problem there. So then, the cosine of A plus B is equal to cosine of A, cosine of B minus sine of A times sine of B. This also is an identity. This equation here is true for all possible values of A and B that we could substitute into this equation. So I'm going to write once again. This is true for all A and B in the real numbers. Whatever A and B we choose, we can plug them into this equation and we will get that the left side and the right side are equal. How about tan? Well, tan of A plus B is simply QS divided by PQ, or sine of A plus B divided by cosine of A plus B. We can see that here. Taking this and substituting into there, we can see that tan of A plus B is sine of A plus B divided by cosine of A plus B. So, let's try and find tan of A plus B. Tan of A plus B is equal to sine of A plus B, I'm going to write in brackets, divided by cosine of A plus B. But we wanted tan of A plus B in terms of sine of A, cosine of B, cosine of A, cosine of B, and tan of A and tan of B. We already know sine of A plus B and cosine of A plus B in terms of those numbers that we want to find. So why don't we just substitute them in? It's true for all A and B, no? So it should be totally fine to do that. So let's do that. Substituting sine of A plus B into the top, we can see that sine of A plus B is equal to sine of A cosine of B plus cosine of A sine of B, and we have to divide by whatever cosine of A plus B is. We have just found cosine of A plus B as cosine of A times cosine of B minus sine of A times sine of B. We have already accomplished our mission. We have expressed tan of A plus B in terms of sine A, sine B, cosine of A, cosine of B, and tan of A, tan of B. In this case, we have again not used tan A and tan B. However, the standard way that we write this third equation is actually in terms of tan of A and tan of B. And we can easily do this conversion to the thing that mathematicians like by simply dividing the top and bottom of this equation that we've just found by cosine of A and cosine of B. So let's try and do that. Taking this to the next page, we'll quickly copy this and take it to the next page so we can solve it. Control C, Control V, and we'll drag it over here. So what we're going to do here is divide the top and bottom both by cosine of A times cosine of B. So we're going to do sine A cosine of B plus cosine of A sine of B. We're going to divide the whole thing by cosine of A cosine of B, and then that whole thing is again divided by cosine of A cosine of B minus sine of A sine of B. And then we're going to divide this thing again by the same number, cosine of A cosine of B. So note, dividing the top and bottom by the same number does nothing to the value. And again, also note that there's an issue here where cosine of A times cosine of B could be 0, in which case we are dividing the top and bottom by 0, but let's just ignore this case for now and carry on. So, dividing the top by cosine of A cosine of B. This first term divided by cosine of A cosine of B will have cosine of b getting cut with this cosine of b, and we'll be left with sine of a divided by cosine of a. Sine of a divided by cosine of a is tan of a, so the very first term gives us tan of a, plus, and then the second term. The second term, when being divided by cosine of a cosine of b, this cosine of a will cut to here. We will have sine of b divided by cosine of b. Sine of b divided by cosine of b is simply tangent of b. So we can write plus tangent of b. The whole thing divided by, and then cosine of a cosine of a cosine of b divided by cosine of a cosine of b will completely cut, giving us just 1. So any number divided by itself is just 1. So we have 1 here, minus, and then we have sine of a sine of b divided by cosine of a cosine of b. So dividing sine of a by cosine of a will give us tangent of a, and dividing sine of b by cosine of b will give us tangent of b. These of course need to be multiplied by each other because we have sine of a times sine of b divided by cosine of a times cosine of b. So then what we will get in the end is tan of a times tan of b here. And because mathematicians like this format, we will stop here. This is the format that we give for tan of a plus b. So we say the tangent of a plus b in terms of sin a sin b cos a cos b and tan a tan b is tan of a plus the tan of b divided by 1 minus tan a tan b. It's somewhat nice that when we have the tangent, we can equate it in terms of the tangent. The sine and cosine still have other sines and cosines in it. The sine of a plus b has cosines in it. It will be quite ugly to turn this cosine into a sine, but we can do it. Recall that sine squared plus cosine squared is equal to 1. We can actually use this identity here. Sine squared theta plus cosine squared theta equal to 1 means that cosine squared theta is 1 minus sine squared theta. So we could technically say that cos theta is plus or minus the square root of 1 minus sine squared theta, and we have an issue here that we have to decide which of these it is. Is it the plus case or the minus case? We have the little problem. So instead of doing that, mathematicians just simply write that we have cosine of theta within that function. So again, this is just because mathematicians like the most clean, most elegant form of writing something. In this case, in the case of sine a plus b and cosine of a plus b, we can nicely, elegantly write that sine of a plus b is sine of a plus cosine of b plus, so sine of a times cosine of b plus cosine of a times sine of b. We can also elegantly write that cosine of a plus b is cosine of a times cosine of b minus sine of a times sine of b. For tangent, we can elegantly write that tan of a plus b is equal to tan a plus tan b divided by 1 minus tan a tan b. That's the whole point. The point is elegance. So there we are. This is our identity that we are going to use for tan of a plus b. We're going to put a box around it because it's the identity. This thing is also true for all a and b in the real numbers. So it's also an identity. There's another set of 3 identities that we're going to get from this, that are sine of a minus b, cosine of a minus b, and tan of a minus b. Currently we have, when we are adding 2 angles together, in a little bit we are going to do subtracting 2 angles from each other. Before we get to there, I want to point out the use case of these identities. So we can do sine of a plus b, cosine of a plus b, and tan of a plus b. This is useful if we want to find tan values, sine values, and cosine values that we do not know. For example, let's say I wanted to find the sine of 75. We do not directly and easily know the sine of 75, which is why it's a little bit of a difficult thing to do. However, with our new formula, we can simply write that sine of 75 is equal to sine of, we can break the 75 into 30 plus 45. And we know what the sine of 30, cosine of 30, and sine of 45 and cosine of 45 are. Using our formula, the sine of a plus b is equal to sine of a, which in this case is 30, times the cosine of b, which in this case is 45, plus the cosine of a, which is this in this case 30, times the cosine of times the sine of b, which in this case is 45. We know all of these values. We know sine of 30 is a half, we know cosine of 30 is 1 over root 2, plus we know cosine of 30 is root 3 divided by 2, and we know sine of 45 is 1 over root 2. I'm sorry, I believe I said cosine of 30 when I was talking about cosine of 45. Cosine of 45 is 1 over root 2. So now solving this, we can get that the sine of 75 is 1 divided by 2 root 2 plus root 3 divided by 2 root 2, which is 1 plus root 3 divided by 2 root 2. And if you're one of those people who's allergic to having roots in the denominator, you can multiply the top and bottom by root 2, and then on the top you can get root 2 times 1 plus root 3. On the bottom you get 2 times root 2 times root 2, which is 2 times root 2 squared, which is 2 times 2, which is 4. So 4 on the bottom, and we can finally write that this is equal to root 2 plus root 6 divided by 4. For those of you who are allergic to root 2's or other roots in the denominator, I've helped you. There is your equation for the sine of 75 degrees using the method of sine A plus B is equal to sine A cos B plus cos A sine B. We can of course do the same exact thing for cosine and tangent. And with the next formula we're going to introduce, we can do even more. The next thing we're going to introduce is the sine of A minus B, the cosine of A minus B, and the tangent of A minus B. So for sine of A minus B, cos of A minus B, and tan of A minus B, there's actually two ways that we could do it. We could either construct a triangle like we did earlier, where we have a total angle of A and part of that angle is B, or we could do it in a different way, where we say, for example, sine of A minus B, I could write sine of A minus B as sine of A plus negative B. There's nothing stopping me from writing like this, and this is absolutely correct. So, using this method, I can write sine of A plus B is sine of A cos of B plus cos of A sine of B. So, sine of A plus negative B would be sine of A cosine of negative B plus cosine of A sine of negative B. Now here, to solve from here to the next line, we are going to apply the two identities which we have discussed in lesson number 5, circular functions. In lesson number 5, circular functions, we discussed that the sine of negative anything is equal to negative the sine of that thing, and the cosine of negative theta is equal to the cosine of theta. If you have forgotten this or simply did not watch that video, there's a card in the top right. You can click it and go to that video. The timestamp should be about 40 minutes in. I'll write the exact timestamp in the card, and you can click it and find that exact time. So, substituting these two, the fact that sine of negative an angle is equal to negative of that sine of that angle, and cosine of a negative angle is equal to the cosine of the angle, gives us that this is equal to sine of A remains as itself, cosine of negative B is equal to cosine of B, plus cosine of A is equal to cosine of A, and sine of negative B is equal to the negative sine of B. So to multiply cosine of A by the negative sine of B. So taking this negative sign outward and into this middle here, we can write this as sine A cos B minus cos A sine B. So there we have a formula for sine of A minus B. Sine of A minus B is equal to sine A cos B minus cos A sine B. Recall, sine of A plus B is equal to sine A cos B plus cos A sine B. The plus has now become a minus in the negative formula. Sine A plus B is equal to sine A cos B plus cos A sine B, and sine A minus B now we have determined is equal to sine A cos B minus cos A sine B. And this here is also an identity, so we can put a box around it. This is true for all A and B in the real numbers. So we can write for all A comma B element of the real numbers. We can do a similar thing for the cosine identity. Considering cosine of a minus b, we can consider cosine of a minus b to be cosine of a plus negative b. Now applying the formula we know for one angle plus another angle, this is equal to cosine of a times the cosine of the other angle, which is negative b, minus sine of the first angle, which is a, times sine of the second angle, which is negative b. This is coming directly by substituting what we found for cosine of a plus b. So cos a plus b is equal to cos a cos b minus sine a sine b. Directly substituting negative b into there, we get this equation. And now once again applying those two identities, the cosine of negative angle is equal to the cosine of that angle, and the sine of a negative angle is equal to negative times the sine of that angle. We have cosine of a remains by as itself, cosine of negative b is equal to cos b, and then minus sine of a times the sine of negative b, which is negative times the sine of b. Now distributing this negative outward, when this negative is distributed outward, it will cancel with the other negative, leaving us with simply cos a cos b plus sine a sine b. So here we can see the plus the minus previously has turned into a plus, because sine of negative b is negative sine of b. And then we can write on the left, cosine of a minus b is equal to cos a cos b plus sine a sine b. Recall, cos a plus b was equal to cos a cos b minus sine a sine b. And this also is an identity. If we have any a and b angles, this will always be true. So we can say once again, for all a and b in the real numbers. Now furthermore, in similar fashion, we can find it for tan also. Considering tan of a minus b, tan of a minus b is tan of a plus negative b, and then substituting we get tan of a plus b is tan a plus tan b divided by 1 minus tan a tan b. So this tan of a plus negative b would be tan of a plus tan of negative b divided by 1 minus tan of a times tan of negative b. So here again recall from that previous video also we have found this, tan of negative theta is equal to negative tan of theta. This can be found by the previous two as well, because tan of negative theta is sine of negative theta divided by cos of negative theta. Sine of negative theta is negative sine theta, and cos of negative theta is cos theta. So we end up with negative sine theta divided by cos theta. Sine theta divided by cos theta is tan theta, so we have negative tan theta. So now substituting this, the fact that tan of a negative angle is equal to negative the tan of that angle, which means that tan of a is tan of a, and then tan of negative b is negative tan of b, so minus tan of b, divide by 1 and then minus tan of a, and we have tan of negative b, which is negative tan of b. I'm going to take an extra step to simplify this. This negative can be taken out and multiplied by this negative, which will leave us with a positive. So finally we can write tan a minus tan b divided by 1 plus tan a tan b. And there we have it. On the left hand side we have tan of a minus b. This is equal to tan a minus tan b divided by 1 plus tan a tan b. Recall again that tan of a plus b was tan a plus tan b divided by 1 minus tan a tan b. And this right here is also an identity. This is true for all a and b that we can find. So you can say this is true for all a comma b, which are elements of the real numbers. So that's that for all of these. Now we know how to add two angles, we know how to subtract angles and get the sine, cosine and tangent in each of those cases based on sine, cosine and tangent of the two numbers, two angles a and b. So now let's look at a few special cases of this. For a few special cases, considering sine of a plus b. A special case would be when a is equal to b, i.e. we want to find sine of a plus a. But sine of a plus a is just sine of 2a. So the special case we're going to consider here is the case where we want to find sine of 2a. How do we find the sine of double of an angle given that we know the angle? Well, the sine of 2a would be just the sine of a plus a. So we can just substitute a and a as our two angles into our formula for the sine of a plus b. So the sine of a plus b is sin A cos b plus cos A sin b. Substituting both of these as a, we get sin A cos A plus cos A sin A. Note that both of these are exactly the same product. So we have 2 times sin A cosine A. So that means the sine of double of an angle, sine of double of any angle, is equal to double of the sine of the angle times the cosine of the angle. This is also an identity. So we put a box around it like this. This is an identity. This is true for all a element of the real numbers. For any a, this relationship is valid, that sine of 2a is equal to 2 sin A cos A. It is a special case of the sine of a plus b. So similarly, for cosine of 2a, we can derive a similar expression. If we do cosine of 2a, cosine of 2a would be equal to cosine of a plus a. So cosine of a plus b is cos A cos b minus sin A sin b. So when a and b are both the same, we have cosine of a times cosine of a minus sine of a times sine of a. So this is cosine squared a minus sine squared a. So then we have that cosine of 2a is equal to cosine squared a minus sine squared a. Now this would be it and this would be the end, but there's this little thing that we people like to do for some reason. We have the urge to convert this into different formats, and we use the identity that we found all the way up here, a couple pages further, even further. Sine squared plus cosine squared of any theta is equal to 1. We use this identity to transform this other identity into two other forms. So we transform this thing into two other forms using the identity sine squared plus cosine squared of any angle a or theta is equal to 1. Considering this thing, what will happen if I add a cosine squared and subtract a cosine squared of a? Well, we get cosine squared a plus cosine squared a minus cosine squared a, because remember we're adding and subtracting the same thing, and then minus extra sine squared a that we had earlier. So here what we do, we group these two cosine squared a's together and we write 2 cosine squared a, and then here we have minus cosine squared a minus sine squared a. If we group it, it is minus in brackets sine squared a plus cosine squared a. So sine squared a plus cosine squared a, which we then write as 1, because recall sine squared plus cosine squared of anything is equal to 1. So this is 2 cosine squared a minus 1. This is one of the other formats that we write this thing in. So we write this as also 2 cosine squared a minus 1. Now I hope you understand that 2 cosine squared a minus 1 and cosine squared a minus sine squared a mean exactly the same thing, because in order to get from this expression to this expression, all we used were identities. All we used were simple identities. So now I can erase this scratch work and go to the other scratch work. So we actually write this in another format as well. we also write this thing, cosine squared A minus sine squared A, in a different format. This time, instead of adding and subtracting a cosine squared A, we add and subtract a sine squared A. So we do cosine squared A, we add a sine squared A, we then subtract a sine squared A, and then there's the extra subtracted sine squared A that we had originally. This is the original, this is the original, and these two were added and subtracted, which means nothing has changed. We have the same exact thing as we had earlier. But now what we do is we pair these two together. We have minus sine squared A and minus sine squared A. So this is minus 2 sine squared A. On this side we have cosine squared A plus sine squared A, and recall the identity cosine squared plus sine squared is equal to 1. So here we can write this part as 1. So now we have 1 minus 2 sine squared A, and that is also equal to the original expression of cos 2A. So we can write is also equal on this here, right side is also equal to 1 minus and then 2 sine squared A. So we do these three formats for cosine of 2A, and I want you to understand that all of these three expressions are the exact same thing, because to get from one expression to another expression, all you need to use is identities, trigonometric identities. So we can write the cosine of 2A as cosine squared A minus sine squared A, or 2 cosine squared A minus 1, or 1 minus 2 sine squared A. Each of these are the exact same identity, and all of these are true for all A in the real numbers. And now let's go to tan. If we consider tan of 2A, or the double angle of tan of 2A, we get that tan of 2A is tan of A plus A. Recall that tan of A plus B was tan A plus tan B, whole thing divided by 1 minus tan A tan B. So substituting that, we get tan A plus again tan A divided by 1 minus tan A times tan A. So here we can group some things together. Tan A plus tan A can be written as 2 tan A divided by, and then tan A times tan A can be written as tan squared A. So we have 1 minus tan squared A. So we have the tan 2A is equal to 2 tan A divided by 1 minus tan squared A, and this is our other identity that we have derived. So this is also an identity. This is true for all A in the real numbers. So these are the sets of identities that we need to remember most likely, but also understand. And I would recommend you take your time, and also the link to this PDF containing all the notes that I've written while teaching this video will be in the comments down in the description down below. Please take a look at it and familiarize yourself with these identities and try to understand them and potentially memorize them as well for your handy usage of these formulas, because these formulas are used quite a lot within the mathematics papers. So now we've discussed sine of A plus B, cosine of A plus B, tangent of A plus B, sine of A minus B, cosine of A minus B, and tangent of A minus B. In our syllabus, we have a couple other formulas that we are expected to know and potentially use. They are how to write the sine of one angle, which I'll say C, plus the sine of another angle, which I'll say D. We're expected to know how to write this in terms of sine of some angles of C and D, cosine of some angles of C and D, and so on. Similarly, sine of C minus sine of D, we're expected to know how to write cosine of C plus cosine of D, and cosine of C minus cosine of D. Cosine of D. So these four identities are, you can see, clearly different from the previous identities that we found. Previously found sine of A plus B. Now we are expected to find sine of C plus sine of D. But actually, the identities that we found above are going to be quite useful in proving these four. So let's get started. We'll start with sine C plus sine D and try to figure out a way to do it. So to attack sin C plus sin D, we want to have sine of one value plus the sine of another value equal to what? Let's go back and remember some identities that we discussed earlier. We know what sine of a plus b is. Sine of a plus b is sine of a times cosine of b plus cosine of a times sine of b. We also know what sine of a minus b is. Sine of a minus b is sine of a times the cosine of b minus the cosine of a times the sine of b. So, what we actually do to try to get sine of c plus sine of d is actually take this first formula, write it as equation 1, and write this second formula and call it equation 2. And then what we do is we add the two together. So we add 1 plus 2. And when you add 1 plus 2, we get an equation of sine of a plus b plus sine of a minus b. On the left side of this equation, we have sine a plus b plus the sine of a minus b. On the right side, let's analyze what we have. So we have sine a cos b plus cos a sin b plus sine a cos b minus cos a sin b. So if you add both left sides together, we can see adding both left sides together, this minus cos a cos sin b cuts with this plus cos a sin b. So we get the two cos a sin b's cancelling each other out, which means we don't have any cos a sin b in our final right hand side. And here we have sin a cos b and another sin a cos b. So when added together, this will give us 2 sin a cos b. So we have 2 sin a cos b on the right side and no cos a sin b is on the right side. So that's gone. So therefore, sin a plus b plus sin a minus b is 2 sin a cos b. Now we're almost done with our formula. We wanted sine of one angle plus sine of another angle equals what? But here we have instead sine of angle A plus angle B plus the sine of angle A minus angle B. So it would be complete. What we require would be complete if we could redefine A plus B to be our angle C, and we could redefine A minus B to be our angle D. If we did that, then the format that we wanted, the format of sin C plus sin D, would be complete on the left hand side. So redefining like that, we get that sin C plus sin D, substituting A plus B for C and A minus B for D, is equal to 2 sine of A, whatever A is, times the cosine of B, whatever B is. But now note, because we redefined A plus B as C and A minus B as D, on the right side we need to rewrite A and B in terms of C and D. So what we have as simultaneous equations is that A plus B is equal to C and A minus B is equal to D. These are two equations which we can solve if we add the left sides together and the right sides together. On the left side, the plus B and the minus B cut to give us no B's, and the two A's add together to give us 2A. So 2A is equal to, on the right hand side we have C plus D. So therefore adding these two equations gives us that 2A is equal to C plus D, meaning that A A here is equal to C plus D divided by 2. So up here in this expression on the right side, for sin A we need to substitute, instead of A, C plus D divided by 2. So we substitute into here C plus D divided by 2. Similarly, we want to write B in terms of C and D in this formula. Considering these two equations again, if instead of adding the two equations we subtracted the bottom equation from the top equation, we did this like this, what we have on the left side is A plus B minus A minus negative B. Minus negative B is plus B, so we have A plus B minus A plus B. We have A minus A which cancels out. On the left side we have A plus B minus A plus B. These two cancel out, leaving us with just a plus B and a plus B, which is 2B. So 2B. On the right side, we subtract D from C, which means we have C minus D. So therefore 2b is equal to C minus D, meaning b is equal to C minus D divided by 2. Substituting this into the above formula, we have C minus D divided by 2 instead of b. And we are done. We are done now. We now have a formula for the sine of one angle plus the sine of another angle is equal to what? In terms of some sine and cosine of those angles. So here we have that the sine of C, where for some angle C, plus the sine of D for some angle D is equal to 2 times the sine of C plus D divided by 2 times the cosine of C minus D divided by 2. So we can use this to find the sine of one angle plus the sine of another angle. This is what we call a sum to product formula. On the left side we have sum of certain trigonometric functions of certain angles. On the right side we have a product of trigonometric functions of certain angles. This is one of the three. We have another one of the four. We have another three to cover. We'll go to those now. But this right here is true for all C and D in the real numbers. So therefore this is also an identity. Moving on to the next one. What we wanted next is sin C minus sin D. So similarly, as we have sin C, some angle C, plus sin D for some angle D, we also want sin C minus sin D for some angles C and D. We want this equal to something. So here, in a similar vein to what we did earlier for the sine of A minus B is simply to replace negative b with plus negative b. Instead of writing sine A minus b, we wrote sine of A plus negative b. We could do that here also, but I'm actually going to avoid doing that. Instead, to get sine of C minus sine of D, instead of doing 1 plus 2 like this, I'm going to do 1 minus 2 because that's what we want. So considering 1 minus 2, let's see what we have. So if you recall, 1 was sin A plus B on the left side, 2 was sin A plus A minus B on the left side. So that therefore the left side of 1 minus 2 will be sin A plus B minus sin A minus B is equal to. On the right side, let's see what we have. So what we want to do here is subtract 2 from 1. So here everything on this side will get multiplied by minus 1. It will get subtracted from the top. Now looking at what's happening here, on the top we have sin A cos B and we're subtracting a sin A cos B. So these two will cancel out. And on the right side we can see there's a cos A sin B here and a negative cos A sin B here, which we are supposed to subtract. So subtracting a negative value is same as adding the value. So here we actually have a plus cos A sin B on the bottom. So we have cos A sin B plus cos A sin B. So given that, what we have on the right side for this equation of 1 minus 2 is cos A sin B plus cos A sin B, which is 2 cos A sin B. So this is our equation. Now once again, we do not want sin A plus B minus sin A minus B. We want sine of some angle C minus sine of some angle D. So what we'll do here, same exact thing. We'll replace this angle with some label which we'll call C, and we'll replace this angle with some label which we'll call D. So here, now rewriting the left side, we have sin C minus sin D, which is the format that we want. And on the right side, we have 2 times the cosine of A times the sine of B. Now here, since we want the equation in terms of C and D, we need to replace A in terms of C and D and B in terms of C and D. So you will see these two are the exact same equations that we had earlier. A plus B is equal to C and A minus B is equal to D. So in this case, we already know the two substitutions we need to make, so I'm not going to actually go through the steps to derive it. A is equal to C plus D divided by 2 and B is equal to C minus D divided by 2. So substituting this into this equation here, we can see that this is 2 cosine of C plus D divided by 2 times the sine of C minus D divided by 2. And this here is also an identity. So we have another identity. We have the identity for sine of some angle plus sine of another angle, and we have the identity of sine of some angle minus the sine of another angle. This is also identity, so I'm going to write down here. This is true for all C, D elements of the real numbers. So now we have sine of some angle plus sine of another angle, and we have sine of some angle minus sine of another angle. We are also trying to find cosine of some angle plus cosine of another angle, and the cosine of some angle minus the cosine of another angle. So to do this, we're actually going to use, again, in similar fashion to the first thing that we did for sine of C plus D and sine of C minus D, we're going to first consider cosine of A plus B and cosine of A minus B. So if you recall from above, we found that the cosine of A plus B is cosine of A times cosine of B minus the sine of A times the sine of B. And you'll also recall that the cosine of A minus B was found to be cosine of A cosine of B plus the sine of A times the sine of B, or you can say minus the sine of A times the sine of negative B, which is plus sine of A sine of B. So we have this. I'm going to call this equation number 3. I'm going to call this equation number 4. Can you guess what we're about to do? The exact same thing that we did up there. We're going to do 3 plus 4 and consider what that gives us. So we're going to try to find cosine of C plus cosine of D. To do that, what we're going to do is consider 3 plus 4 and see what we get. On the left side, we have cosine of A plus B and a cosine of A minus B. So adding the two together, we have cosine of A plus B plus the cosine of A minus B is equal to something. So what's it equal to? Well, considering the right hand side, we have cosine of A times cosine of B minus sine A sine B, and another plus cosine of A cosine of B plus sine of A sine of B. So here, if we add the two right hand sides together, these two will cut because we have minus sine A sine B and plus sine A sine B, so they are gone. And these two cosine of A cosine of B's will add together. So we have 2 cosine of A cosine of B's, which means the right hand side is equal to 2 cosine of A cosine of B. And now, since we don't want cosine of A plus B plus cosine of A minus B, we want cosine of some angle C plus cosine of some angle D. We are simply going to replace the symbol A plus B with the symbol C and the symbol A minus B with the symbol D, which then on the left side will give us cosine of C plus cosine of D. Now we need to replace the right side's two variables A and B in terms of C and D. Again, these are the exact same two equations that we had above. A plus B is equal to C and A minus B is equal to D, whose solutions are A is equal to C plus D divided by 2 and B is equal to C minus D divided by 2. So here, substituting these two into the below equation, we can see that cosine of C plus cosine of D is equal to cosine of A is C plus D divided by 2 times the cosine of B is C minus D divided by 2. Hence, we have derived an equation of cosine of C plus cosine of D is equal to what? We have derived another sum to product formula. This is also an identity because this is true for all C and D that you can think of within the real numbers. So I'm going to write that also on the right side for all C, D element of the real numbers, meaning that this is an identity. Now similarly, as you can probably guess, the next thing we're going to do is find cosine of C minus cosine of D as a product formula. So let's do that. To do that, of course, we're going to use the exact same strategy that we did for the sine. We're going to, instead of considering 3 plus 4, consider 3 minus 4. So let's now consider 3 minus 4. 4 cosine of C minus cosine of D equal what? Let's consider 3 minus 4. So considering 3 minus 4, on the left side we have cosine of A plus B minus cosine of A minus B. So we can write this is cosine of A plus B minus the cosine of A minus B is equal to what? on the right side we have cos A cos B minus sin A sin B minus the entirety of the second equation's right hand side. Doing this, so here we can see with this minus, this cos A cos B cuts to this minus cos A cos B, and distributing this minus into here we can see we have minus sin A sin B plus another minus sin A sin B. So we have minus sin A sin B minus another sin A sin B. So adding these two minus sin A sin B's together, we get on the right hand side minus 2 sin A sin B. Alright, all good. Now all we need to do is replace the variables, because we don't want cosine of A plus B minus cosine of A minus B. We want cosine of some angle C minus cosine of some angle D. So replacing A plus B with C and A minus B with D, we can write that cosine of C minus cosine of D for some angle C and D is equal to negative 2 sine of whatever A is times the sine of whatever B is. Now recall, we want to redefine A and B in terms of C and D, because we want the formula to be in terms of C and D. So again, same exact two equations, I'm not going to bother solving it. A is C plus D divided by 2 and B is C minus D divided by 2. And there, this is the formula that we want. This is also an identity, so we put a box around it. This is not necessary or standard, by the way. Putting the box around it is my own thing that I use to show identities. And I'm going to say this is true for all C, D element of the real numbers. So we're almost done with the set of identities that we need to know. There's another two that are special regarding to triangles, which we will go through. But for now, again, try to go back to each of these four: sine of C plus sine of D, sine of C minus sine of D, cosine of C plus cosine of D, and cosine of C minus cosine of D. Try it for yourself by considering certain angles C and D and see what the values are for yourself. And I would also recommend that you yourself prove these on your own with a piece of paper and a pen to help better absorb them into your mind. Alright, let's go to the next two identities that we're going to talk about, the final two within this lesson, and conclude the lesson. The two identities that we're going to talk about have to do with triangles. Consider a triangle, any triangle. So drawing a triangle, I'm going to draw one. Here is some random triangle. Let's make it a little different shaped than normal. There we go. So this triangle here is going to be the triangle A, B, C. So recall the convention of having a triangle with points of A, B, C, and then calling the angles at each of those points by the same capital letter names. So this angle here is what I mean when I say angle capital A. This angle here is what I mean when I say angle capital B, and this angle here is what I mean when I say angle capital C. So let's now consider what A plus B plus C is. A plus B plus C. Well, we have a triangle. As we know since probably 6th grade, when you have a triangle, the sum of the internal angles of the triangle is 180 degrees. But now we're dealing with radians because we are adult human beings now. We are no longer going to deal with silly degrees, we're going to deal with radians, and 180 degrees is equal to pi radians. So therefore, angles A plus B plus C must be equal to pi radians. So we have that A plus B plus C is equal to pi. So now, considering this, A plus B plus C is equal to pi, let's consider what the sine of A plus B is. The sine of A plus B for any two of the angles A and B. Understand here that it doesn't matter which side is side A, which angle is angle B. Without loss of generality, this can work for any set of triangles, any definition of the angles. So here, consider sine of A plus B. Sine of A plus B is the same as sine of pi minus C. Why is this? Well, obviously, because A plus B plus C is equal to pi, meaning that A plus B is equal to pi minus C in terms of angles. So therefore these quantities have to be the same thing. And also recall from this our trigonometric identity video that we did earlier, where we considered circular functions, lesson number 5, we found that sine of 180 degrees or pi minus the angle is equal to the angle sine. So here this is equal to sine of C. So therefore sine of A plus B is equal to the sine of C, is equal to the sine of C. So any triangle, no matter which triangle you choose, pick any two of the sides and find their angles, and then you will get the result that the sine of the sum of two angles in a triangle is equal to the sine of the third angle. So we have this property. We can also prove this property from our sum formula that we found earlier. Recall the sine of C A minus B is what? The sine of A minus B is equal to sine A cos B minus cos A sine B. So now recall, substituting sine of pi minus C into here, sine of pi minus C is equal to sine of pi cosine of C minus cosine of pi times sine of C. So here the sine of pi is 0, so this is 0, so 0 times the cosine of C is here, minus the cosine of pi is negative 1 times the sine of C here. So here solving this, we get that the sine of pi minus C is equal to 0 times cosine of C, which is 0, minus negative sine of C, which is just sine of C. So therefore sine of pi minus C is equal to sine of C. We have proven it not only in the previous lesson in which we proved it simply by using geometry, we also proved it using a formula here. So here within any triangle, selecting any two sides within the triangle, any 2 points within the triangle, finding their angles, adding the two angles together and taking the sine of it will be equal to the sine of the third angle within the triangle. This is one identity. Now we can do this for cosine of also, but cosine will not give us something nice. The cosine, it kind of does give us something nice, not exactly the nicest thing. The cosine of A plus B is the cosine of pi minus C, which is actually the negative cosine of C. And we can show this if we again use the formula of cosine of A minus B. So cosine of A minus B is equal to cos A cos B plus sin A sin B. Substituting that into here, the cosine of pi minus C is equal to the cosine of pi times the cosine of C plus sine of pi times the sine of C. So here substituting the values, cosine of pi is negative 1, cosine of C is cosine of C, sine of pi is 0 times sine of C. This becomes 0. We are left with negative 1 times the cosine of C, which is just negative cosine of C. So this is what I said. For the cosine, it's somewhat nice, but it's not exact. It's negative of that value. The cosine of A plus B for any two angles within the triangle A and B is equal to the negative cosine of the other third angle C. So these two are two identities which exist within a triangle. These work for any angles within the triangle. So this is not exactly 100% identity because it doesn't work across all the real numbers, but it works within any triangle, so we kind of do consider it as an identity. This is a trigonometric identity specifically for closed triangles. So another identity that we have for triangles is this other one, which is what we get when we consider the sine of the sum of two angles within the triangle A plus B, but then divide by 2. And similarly the cosine of any two angles within the triangle sum together, divide by 2. So here we can see, since the sum of all three angles is equal to pi, the sum of any two angles is pi minus third angle. So then we can write this as the sine of pi minus c divided by 2, because a plus b is equal to pi minus c. Similarly, the cosine can be written as the cosine of pi minus c divided by 2. So we can split this fraction and say that this is equal to the sine of pi by 2 or 90 degrees minus c divided by 2. So not c divided by c divided by 2. Similarly, on the bottom we can split the fraction and call this sine of pi by 2 minus c divided by 2. So now recall again in the trigonometric identities video within the circular functions, lesson number 5. Again recall that when we had sine of 90 minus an angle, it was simply equal to the cosine of that angle. So this is actually equal to cosine of c divided by 2. Similarly, recall cosine of 90 minus an angle was equal to the sine of that angle. So this is equal to sine c divided by 2. We can also, of course, if you really want to try, you can try to use our sum of angles formulae to solve this as well. Consider sine of pi by 2 minus c by 2 and substitute it into the sine of a minus b formula, which we'll actually quickly do as a demonstration to show that our theory works. Sine of pi by 2 minus c by 2, sine of pi by 2 minus c by 2 is equal to sine of pi by 2 cosine of c by 2 minus cosine of pi by 2 sine of c by 2. The sine of pi by 2 is equal to 1 times the cosine of c by 2 minus the cosine of pi by 2 is equal to 0 times the sine of c by 2. So here this part becomes 0. What we are left with is 1 times cosine of c divided by 2, which is cosine of c divided by 2. And well, look at that. Our theory agrees with our other theory. That means both theories are either correct or both theories are wrong. But we know at least one of these theories are correct because we can do successful calculations with it. So therefore, both theories must be correct. So there we've shown that sine of pi by 2 minus c by 2 is equal to cosine of c by 2. Similarly, if we use the other formula for cosine of pi by 2 minus c by 2, we can see that cosine of pi by 2 minus c by 2. Oh, by the way, if you're curious why I'm doing this, it's just as a proof of concept to show that mathematics actually works. So here, if we consider cosine of pi by 2 minus cosine minus c by 2, this is cosine of pi by 2 times cosine of c by 2 plus sine of pi by 2 times the sine of c by 2. The cosine of pi by 2 is equal to 0 times the cosine of c by 2 plus the sine of pi by 2, which is equal to 1 times the sine of c by 2. So here this part goes to 0 here, which leaves us with just 1 times sine of c by 2, which is sine of c by 2. And well, look at that. One of our theories agrees with another one of our theories. So either both are correct or both are wrong. Most likely both are correct because we know at least one of these is correct because it works. We get the correct answers when we try it with real numbers. So there, again, with our other theory, we have also shown that cosine of a plus b divided by 2 is equal to sine of c by 2 within a triangle ABC. So these two identities work within triangles ABC, and therefore they are also considered identities because they work for any triangle with angles A, B and C. So that will conclude our lesson for today. Let's summarize what we talked about. I'm not going to write any of the formulae, but let's summarize what we talked about. We talked about what an identity is. An identity is an equation that holds true for all possible values of the inputs. And then we derived 3 Pythagorean identities. One that we had simply sin²θ plus cos²θ is equal to 1. Another one that we got by dividing both sides by sin²θ, we got that 1 plus cot²θ is equal to cosec²θ. Here we momentarily pause to talk about the fact that we write cosec like this and lots of places write cosec as CSC. Then we divided the sin² plus cosine² equal to 1 formula by cosine²θ to get tan²θ plus 1 is equal to secant²θ. After deriving these 3 Pythagorean identities, we then moved on to different set of identities considering the sum of 2 angles as sine, cosine and tangent. We found the sine of a plus b, which if you don't remember, go up and check it. We found the cosine of a plus b, and we found the tangent of a plus b in terms of sin A cos A sin B cos B and tan A and tan B. So here we have tan A plus B. We also found, similar to this, the sine of one angle A minus another angle B, the cosine of one angle A minus an angle B, and the tangent of one angle A minus another angle B. And then we found special cases of this where we have A and B being equal, so we found sine of A plus A, or sine of 2A, which I'm going to actually write here in this summary as sine of 2A. Then we found the cosine of 2A, and finally we found the tangent of 2A. Now with this, we then moved on to a different sort of subtopic. We tried to find if we can write the sine of one angle C, sine C, plus the sine of another angle D in terms of C and D's sines and cosines. We did. We also found sine of C minus sine of D in terms of that same method. We also found the cosine of some angle C plus the cosine of some angle D, and the cosine of some angle C minus the cosine of some angle D in terms of the sines and cosines of certain combinations of C and D. We then, as a final conclusion, talked about when we have a triangle which we label with the points A, B and C, what kind of equations we can derive within these angles. We found out that A plus B plus C was equal to pi radians. Using that, we found that sine of A plus B was in fact equal to sine of C for any two angles A and B summed together, equaling the third angle within the triangle C. We similarly found that cosine of A plus B was equal to the negative cosine of C, which is not that nice, but it's also true. And we also found that the sine of any two angles summed together divided by 2 is equal to the cosine of the other angle divided by 2. Similarly, we found that the cosine of any two angles within the triangle summed together divided by 2 is equal to the sine of the third angle divided by 2. And that concludes the lesson for today. Thank you for watching all the way up to the end, and goodbye.